Welcome to this Pacta Cobol video. Today we'll show you the importance of the Cobol programming language in the world. If you want to learn Cobol, keep in mind that traditional training methods, like watching YouTube tutorials or Udemy courses, are far too passive to help you make real progress. On cobol.pacta.com, you'll find many excerpts from our Cobol training programs, along with detailed explanations of the Pacta Codex method. Pacta Cobol courses are specially designed for beginners. Subscribe to our channel, share our videos, leave your comments, and start your training today.
Welcome to the Deep Dive. We're here to peel back the layers on complex topics, find those surprising nuggets of knowledge. And today, we have something that honestly sounds a bit like science fiction, but it's very real. It impacts your life like every single day.
Okay, I'm intrigued.
Imagine a programming language. It was conceived, get this, 65 years ago.
Wow, 1959. That's ancient in tech terms.
Exactly, 1959. And it quietly, invisibly processes something like $3 trillion in global transactions every single day.
3 trillion.
Yeah. It's the hidden engine, they say, behind over 80% of the world's in-person financial stuff. Yet, you can barely find a school that teaches it anymore.
That's quite a paradox. The backbone of finance, and nobody learns it.
Right. It's like this digital ghost in the machine running critical infrastructure globally, and, well, almost no one knows its name, let alone how to write in it.
Cobol.
Cobol, that's the one. So this deep dive, it's really for you, the learner, to understand this paradox. Why is this dark horse language still so vital? Why is there this, escalating shortage of developers? And maybe the most exciting part, how a really innovative new method, it's called Pacta Codex, how it's shaking things up.
Revolutionizing education, potentially?
Yeah, potentially all programming education, starting with Cobol. So if you've ever felt lost in, online tutorials or just overwhelmed.
That tutorial hell feeling?
Exactly. Watching videos but still not being able to build anything. This deep dive, it's going to shine a light on a surprisingly effective new path.
That's good.
Our mission today is pretty clear. We're going to unpack Cobol's unexpected history, its sheer importance. Then we'll dissect the, frankly, glaring gaps in how programming is usually taught.
YouTube, Udemy, the usual suspects.
Those ones. Then we'll unveil this groundbreaking Pacta Codex method. It's rooted in neuroscience, which is fascinating.
Really applying brain science to learning code.
And finally, we'll look at Pacta Learning, their Cobol training program. It's the first real-world test case for this method, and it's becoming a global benchmark.
Okay, setting a new standard.
Yeah. Okay, let's dig in. It's a story of hidden infrastructure and a kind of pedagogical revolution. So, Cobol, this invisible force, it's almost mind-bending when you think about the scale. What's really fascinating, maybe a bit unsettling, is just how deep it runs in our daily lives, even if we never, see it. Can you elaborate on that? Just how ubiquitous is it?
Absolutely. An invisible backbone is really the perfect term for it. Its presence everywhere it's a testament to its original design, its robustness. When we talk about reliance, it's not theoretical. A staggering 43% of all banking systems globally still run on Cobol.
43%, nearly half the world's banks.
Pretty much. Think about that. Almost half the financial transactions buzzing around the planet are flowing through code written, decades ago.
Wow.
But it goes deeper. You use your credit card, your debit card in a store. There's an incredible 80% chance Cobol is somewhere in that processing chain.
80%. So most swipes involve Cobol.
Highly likely. And ATMs, if you're getting cash out. Fully 95% of those ATM and DAB operations, direct access banking, they still need Cobol to work smoothly.
That's just staggering. Every time I swipe my card or use an ATM, I'm trusting this language from 1959. But it's not just finance, is it? I think I heard it's in other critical areas too.
Oh, definitely. Its reach is wide. Beyond finance, estimates suggest over 60% of U.S. health system records are on Cobol-based systems.
Healthcare too. Wow.
Yeah. Wall Street, high-stakes trading relies heavily on it. Global banking systems, obviously. Governments, like the U.S. Social Security Administration, handling benefits for millions.
Critical government functions.
Absolutely. Public utilities keeping the lights on, water running, even huge retail inventory systems, making sure stuff is on the shelves, all heavily dependent on Cobol.
Okay, so it's everywhere.
And the sheer amount of it, estimated 800 billion lines of Cobol code still active globally.
800 billion. That number's hard to even grasp.
It is. And this isn't just, old software gathering dust. It's actively running, sustaining functions that keep delivering reliably at just immense scale.
So given that incredible role, why 1959? What was happening back then in the late 50s that made something like Cobol necessary? Sounds like there were big problems.
Right. The context of 59 is key. Two major hurdles were holding back business computing. First, a huge problem. Limited portability.
Meaning code for one machine wouldn't run on another.
Exactly. Computers back then were massive, super expensive. Programs were mostly in machine language or assembly code tied to that specific hardware. So get a new machine. You had to rewrite everything.
Which must have cost a fortune.
A fortune. In 1959 money, just porting one program could cost $600,000.
Yeah.
Just imagine.
Unbelievable.
And the existing portable languages like Fortran. Great for science, math, but not really built for the kind of verbose, data-heavy work business is needed.
Okay, so portability was a nightmare. What was the other big issue?
That leads right into it. Exorbitant development costs. Just building a new data processing system from scratch could easily hit $800,000.
Wow. So only the biggest companies or governments could even afford it.
Precisely. It was against that background that people like Mary Kay Hawes and others had this vision. A common business-oriented language. And it wasn't just a corporate idea. The U.S. Department of Defense was a major sponsor.
The DoD. Why them?
They faced massive programming costs across all their different systems. They desperately needed standardization, something cost-effective.
A government push for a business solution. Makes sense. So what were the main goals for this new language? What did they want Cobol to do?
The committee had very clear aims. First, simplicity and versatility. It needed to work across banking, insurance, administration, healthcare, you name it.
One language for many jobs.
Right. Second, it had to handle very large amounts of data efficiently. Core business stuff.
Big data, even back then.
In a way, yes. And third, maybe the most revolutionary part, an English-like syntax.
Making it readable for non-programmers.
That was the goal. A huge departure from the symbolic stuff in Fortran. They wanted managers, auditors, admins to be able to read and basically understand the logic. So Cobol was born. Its phrase-like style, ADD 1 to X, move name to address field, it made it accessible. Common business-oriented language. It lived up to the name.
It's just incredible that programs from the 60s are still running, doing critical work. That really says something about its performance, its robustness. This isn't just inertia, is it? There have to be solid reasons it sticks around.
You've nailed it. It's way beyond inertia. It's rooted in fundamental strengths. Cobol was engineered for performance and, crucially, robustness. It was designed for precise, fixed-point calculations.
Fixed point. What does that mean, practically?
Think about money. You need exact decimals, right? Down to the penny. Fixed-point map guarantees that. Unlike floating point, which can sometimes have tiny rounding errors.
Which would be disastrous in finance.
Absolutely disastrous. For financial systems, where every cent counts, that precision is non-negotiable. The fact that code written 60 years ago is still running perfectly, that shows its reliability, the foresight of those designers.
Okay, that precision makes sense for finance. But still, with all these modern languages, Python, Java, you name it, why don't companies just rewrite everything? It seems like the logical move to modernize.
It sounds logical, yeah. But the reality, it's incredibly complex, hugely expensive, and packed with risk.
How so?
Okay, picture a big bank. Millions, maybe hundreds of millions of lines of Cobol. Rewriting even a small chunk, say 10,000 lines in Python, that's a massive project in itself.
Right. Now scale that up.
Exactly. And you're dealing with code that handles interest rates, fees, loans, balances.
Yeah.
The core stuff. If you make one tiny mistake, a misplaced decimal, a slightly off calculation, it could cause huge financial losses. Or in healthcare systems, literally endanger lives.
And finding the original developers, probably impossible.
Often, yeah. They're retired. Documentation might be missing or incomplete. The existing code becomes this kind of black box. It works, but figuring out all its intricate logic is incredibly hard. Translating it accurately, it's like translating poetry, nuances get lost, subtle errors creep in.
So the risk of breaking something critical is just too high.
Very high. So if we connect this to the bigger picture, companies aren't just being stubborn. They often choose to modernize in layers, build modern APIs, new front ends on top of the Cobol core.
Keep the engine, change the dashboard.
Kind of, yeah. It lets them integrate with new tech, offer modern services, but keep that battle-tested, reliable core running. It's a calculated decision. Risk management, cost, stability.
Yeah.
It's pragmatic, not just inertia.
What about security? That's huge today. Are these old mainframe systems running Cobol somehow safer than modern web apps?
That's a great question, and the answer is interesting. Mainframes, where most Cobol lives are inherently centralized, they've been hardened against attacks for decades.
A smaller target.
In a way, yeah. The attack surface is much smaller than, say, a distributed web system with tons of interconnected parts, third-party libraries.
Yeah.
The real risks for mainframes often come from social engineering or insider threats, not typical web exploits hacking the Cobol code directly.
Different kind of threat landscape.
Very different.
Yeah.
And there's stability. Modern tech stacks change constantly. New frameworks, updates, obsolescence. It's rapid fire. Cobol. It evolves slowly, consistently. It's predictable, incredibly stable, secure in a way that's just stood the test of time.
So despite predictions, it's not dying. I remember the whole Y2K panic. That must have been a huge test for Cobol system.
Yes, a massive global stress test, absolutely. And Cobol came through. Y2K, though scary, was an anticipated problem. Huge investments were made globally to fix the code.
And it worked.
It worked. It proved Cobol's adaptability, the skill of its developers.
Yeah.
Now, people talk about future date limits, maybe 2038, 2049. Some systems might need tweaking again.
So it keeps adapting.
Exactly.
Yeah.
Every time these things come up, the idea that Cobol will just vanish gets proven wrong. It just keeps demonstrating its longevity, its resilience.
Okay, so given this enduring importance and the fact it's not really taught, there must be a massive demand for Cobol developers. But where do they come from if universities aren't teaching it? What does this mean for someone maybe looking for a tech career?
This is where it gets really interesting for job seekers.
Yeah.
Especially those maybe wanting a less crowded but very rewarding path. There's a huge and worsening skill shortage.
Because nobody's learning it.
Right. It's rarely, if ever, in standard computer science curricula. Meanwhile, the developers trained back in the 80s, 90s, even earlier, they're retiring. A huge brain drain is happening.
Losing all that experience.
Exactly. Some companies are so desperate, they're actually recruiting people in their late 50s, early 60s, offering permanent contracts just to keep the lights on.
Wow.
The demand for Cobol skills massively outstrips the supply. It creates a very, very favorable job market for anyone who masters it.
High demand, low supply. That usually means good salaries, right? What kind of money are we talking about?
Definitely. Careers are exceptionally stable and, yes, lucrative. In the U.S., the average Cobol programmer salary is around $90,000 a year.
That's a solid salary.
It is, and with experience. Especially if you have dual skills, Cobol, plus modern stuff like Java, .NET, maybe even interface knowledge. It goes much higher.
Like how much higher?
In a big financial center, say Paris, beginners might start around 40K gross hours.
Yeah.
But experienced experts, 110K, 120K, even more is realistic, especially in consulting.
That's serious money.
So what does this mean for you listening? It's a unique opportunity. Stable, well-paid work for, conservatively, the next 10, 15 years. Minimum. It's a safe bet in a field that changes so fast.
That stability is incredibly appealing. What kind of profile are companies looking for? Is it just writing Cobol, or is there more to it?
It's more nuanced than just coding. The ideal candidate often has that dual skill set. Cobol mastery, plus knowing modern languages or interfaces, Java, .NET, maybe JavaScript for front ends. They can bridge the old and new.
Connecting legacy systems to modern tech.
Exactly. Beyond that, Cobol developers often become functional experts. They develop this incredibly deep understanding of the business rules baked into those old systems. They optimize complex batch processes. Sometimes, a key part of the job is even rebuilding lost documentation from the code itself.
Like digital archaeology.
Kind of. It needs technical skill,
Yeah.
business understanding, and, yeah, almost forensic attention to detail.
We hear so much about AI automating programming jobs. Is Cobol safe, or could AI eventually replace these developers too?
That's a really timely question. AI is definitely automating simpler tasks, boilerplate web code, basic scripts.
Right.
But Cobol systems, they're a different beast. The complexity, the interwoven business rules, the massive data volumes, the strict performance needs. It's likely to be one of the last bastions against full automation.
Too complex for current AI.
Understanding, analyzing, and accurately regenerating these intricate mainframe systems. That needs a depth of human insight, contextual understanding. AI isn't there yet. Human expertise, critical thinking, that deep mainframe knowledge, it's going to be vital for a long time.
That makes sense. Okay, one last thing on Cobol itself. Is it actually difficult to learn, or is that just a perception because it's old?
Okay, here's where it gets really interesting, and it's a key distinction. People who actually work with Cobol often say the language itself is pretty simple. elegant even, because of that English-like syntax we talked about.
Designed to be readable.
Exactly. You can often figure out the gist of a Cobol program without being an expert. The perceived difficulty, the real challenge, it usually comes from the whole mainframe ecosystem around it.
Not the language, but its environment.
Right. Things like JCL job control language telling the mainframe what to run, big database systems like IMS or DB2, the whole concept of batch processing, the operational constraints of these high-performance systems.
So a Python developer could pick up Cobol syntax quickly.
Probably, yeah. The syntax isn't the main barrier. But they'd still need to invest serious time learning the mainframe tools, the environment, the whole way of working. That's the real learning curve, the context, not just the code.
That perfectly leads us into the next big piece here, because even with simple syntax, learning to actually code effectively, well, it can be incredibly frustrating. Many people trying to learn, maybe you listening, get stuck in what's called tutorial hell.
Oh, absolutely. Tutorial hell. It's almost a rite of passage, unfortunately. It's that insidious illusion of competence.
Illusion of competence.
Yeah. You watch hours of videos, read books, go through online courses, MOOCs, YouTube, Udemy, and you feel like you're making progress. Everything seems clear while you're consuming the content.
It clicks while you watch.
Exactly. But then you face a blank screen, a new problem, an unfamiliar task, and suddenly you're completely stuck. You struggle.
It's not about being smart or not, is it?
Not at all. It's a symptom. It shows the learning methods themselves are just fundamentally not suited for building a practical, hands-on skill like programming.
You might have felt this yourself, right? Everything makes perfect sense watching the expert code, but then nothing, just staring at the editor. It reminds me of watching, like, a pro athlete.
Good analogy.
Their moves look so effortless, so fluid. You think, I could do that. But watching isn't doing. Real skill in sports or code comes from active practice, deliberate effort, and crucially, learning from mistakes, from failure.
That disconnect is profound. And it's precisely why so many traditional ways of teaching programming, even though they're everywhere, just fall short. Let's look at a few.
Okay.
Take the Fortamies books. They're great at demystifying things. Right? Simple language, linear steps, easy analogies. Excellent for building basic declarative knowledge.
Declarative meaning.
Knowing what? Knowing the definition of a variable, what a specific Cobol command does.
Yeah.
Facts.
Got it. Facts.
But the downsides are significant. It's very passive. Few real exercises, almost no immediate feedback. Concepts are often taught in isolation, not in the context of a real project. They teach you facts, but not really how to use them together dynamically.
Okay, so good for basics, but limited practice. What about something like the Head First series? They seem more engaging, more visual, brain-friendly, they call it.
Yeah, Head First is a big step up pedagogically. They consciously use cognitive science principles, things like dual encoding text and strong visuals. They use the generation effect, making you guess before giving the answer, which engages your brain more.
Makes you think actively.
Right. Varied repetition, conversational style that helps reduce extrinsic cognitive load. Yeah, it's the mental effort of just dealing with the learning material itself, like wading through dense text.
So easier to process the information.
Much easier. They're fantastic for solidifying that declarative knowing what. But it's still a static book. The practice is simulated, not truly authentic. And crucially, it can't give you that real-time specific feedback you need to build procedural skill.
Procedural skill being?
Knowing how, the actual fluency, the ability to write code effectively, to debug, to structure solutions, the doing part.
So Head First helps understanding, but still doesn't fully bridge the gap to doing. Which brings us to the big ones. MOOCs, Udemy, YouTube, the main sources of tutorial hell for many. What's fundamentally wrong there, cognitively?
That really gets to the heart of it. Why does watching hours of videos create this powerful but ultimately false sense of mastery?
Yeah.
It boils down to a mismatch with how our brains actually learn practical skills. First, there's that illusion of competence again.
How does watching trick us?
Watching mostly activates recognition memory. You see the code, you understand it, your brain goes, yep, seen that, know that. But building lasting skill, consolidating memory, that relies heavily on active recall, on trying to retrieve information yourself, making mistakes, and getting feedback.
Videos don't force recall.
Nope. The instructor does the heavy lifting, the problem solving. Your brain is mostly just observing, recognizing patterns. It feels like learning, but it's shallow.
And feedback. You mentioned that's critical in programming. Code breaks easily.
Exactly. Programming is inherently error dense. You miss a comma, a bracket, boom. Without a compiler or tests or a reviewer instantly telling you what you did wrong and why, you can easily solidify bad habits without even knowing it.
Videos can't give you personalized error feedback.
Not in real time on your code.
Yeah.
Second big issue, an absence of desirable difficulty. Real learning needs a bit of struggle. Recalling info without hints, applying concepts in new ways, working with incomplete information that forces deeper processing.
Makes the learning stick better.
Right. But linear videos, they often smooth out those difficulties. The instructor makes it look easy, which feels good, but it prevents the robust skill building that only comes from productive struggle.
So just copying the code line by line from the video, that's not enough to solve a new problem later. That explains the blank page fear.
Precisely. It leads directly to poor transferability. Copying an example isn't the same as solving a novel problem. True transfer applying skills in new situations requires varied practice, changing contexts, realistic, even small projects.
Things videos usually don't provide in a structured way.
Generally not. And finally, these passive methods lack metacognitive tools to help you think about your own thinking and learning.
Like what kind of tools?
Structured bug journals to analyze your errors. Checklists for code quality, ways to track your debugging process. These things help you learn, how to manage errors, how to improve systematically. They build self-awareness as a developer. Videos alone just don't foster that.
It really sounds like the core problem is this deep mismatch, how we're taught versus how our brains actually learn practical skills. You mentioned declarative versus procedural memory earlier. Can you break that down more? Why is it so key here?
It's absolutely fundamental. Our brains seem to use distinct systems for different kinds of knowledge. Declarative memory, that's your knowing what. Facts, concepts, rules. Cobol syntax rules, what a class is in Java. The steps of an algorithm.
Things you can state or declare.
Exactly. Stored mainly in the hippocampus, temporal lobes. Books, lectures, videos. They're great at feeding this system. They deliver facts efficiently.
Okay. And procedural.
Procedural memory is your knowing how. Skills, habits, automatic actions. Typing on a keyboard, riding a bike, or structuring code, debugging efficiently, writing clean idiomatic code without thinking consciously about every little rule.
The muscle memory of coding.
That's a good way to think of it, yeah.
Yeah.
It involves different brain areas, basal ganglia, cerebellum, motor cortex. It's built through practice, repetition, feedback. And here's the critical bottleneck, the great filter in learning to code.
Okay.
Effective skill acquisition is the process of converting that declarative knowing what into fluent, automatic, procedural knowing how. And that conversion only happens through active, deliberate practice with feedback.
So traditional resources load you up with facts.
But they fail to provide the structured practice and feedback needed to build the skill, the procedural memory. They get you to stage 1, but can't bridge the gap to fluency. That's where most people get stuck and give up. They know stuff, but they can't do stuff.
That distinction is huge. Knowing the rules versus playing the game well. What about cognitive load? You mentioned that briefly too. How does that play into passive learning's failures?
Right, cognitive load theory from John Sweller. Super insightful. It breaks down the mental effort during learning into 3 types. First is intrinsic load. That's just the inherent difficulty of the concept itself. Some topics are just complex. Can't avoid that.
But like learning recursion, maybe?
Good example. Then there's extrinsic load. This is the mental effort wasted on just processing the teaching material, not the actual concept. Badly designed slides, a confusing explanation, juggling windows, pausing and rewinding a video constantly.
Stuff that gets in the way of learning.
Exactly. Passive tutorials can have really high extrinsic load. You're spending precious brain power just trying to follow along, keep up, manage the interface. Energy not spent on actual learning.
Okay, so intrinsic is the topic's difficulty. Extrinsic is the hassle of the teaching method. What's the third type?
That's germane load, or essential load. This is the good kind of mental effort. The effort involved in deep processing, making connections, building mental models, transferring knowledge to long-term memory. This is the actual learning work.
Where the real understanding happens.
Yes, and here's the trap with passive tutorials. They often maximize the bad load, extrinsic following along is fiddly, while minimizing the good load. Germaine, the instructor, does all the thinking and problem solving for you.
So your brain is busy, but not really learning deeply.
Precisely. Your limited working memory, your mental bandwidth gets clogged up with the mechanics of watching and copying. There's no room left for the deep processing, the germane load needed to build real skill. An effective learning system needs to flip that. Minimize the extrinsic hassle, maximize the germane cognitive work.
Okay, so it's clear. There's this fundamental problem with passive learning, especially for a practical skill like programming, this whole tutorial hell thing. And that frustration, that gap, is what led Elaine Stevens to develop the Pacta Codex method. What was his driving vision?
Elaine Stevens, he's an IT consultant, and he didn't just observe this problem, he lived it. He consumed tons of learning materials, but still felt incompetent. That personal frustration was the spark.
He saw the gap firsthand.
Exactly. He realized the issue wasn't a lack of information out there. It was a lack of effective methodology to turn that information into actual usable skill. His vision wasn't just another course. It was to re-engineer the process of learning programming based on how our brains actually work, to break that cycle of passive watching and false confidence.
And his background, it wasn't initially in programming education, right?
Yeah.
Something about legal text. How did that connect?
That background is actually key. He co-founded Pacta Editions, specializing in complex multilingual legal publications. These weren't just books, they were sophisticated knowledge management tools. They were designed to take declarative legal text, the what of the law, and turn it into procedural skill, the how of drafting solid, effective contracts. It required deep thinking about structuring information, breaking down complexity, and ensuring practical application in a field where errors are costly.
Transforming knowledge into practical skill.
Precisely. Stevens brilliantly saw the parallels and adapted that methodology, structured decomposition, guided application, feedback loops from law to programming. The result is Pacta Learning and the Codex method. He calls it the anti-tutorial. It's engineered expertise building.
The anti-tutorial, I like that. So this Codex method, it's an acronym, right? Conceptualize, operate, debug, explain, explore. How does this loop work? Is it just linear steps?
Good question. No, it's not linear. That's crucial. It's a short, iterative loop. You take each core concept through the full CODEX cycle again and again. The platform guides this. It's designed to systematically forge knowledge into durable, usable skill, a continuous improvement engine for your brain.
Okay, let's break it down. C is for conceptualize. What happens there?
Right. Conceptualize. This is where a new idea, concept, or command is introduced. But it's done minimally. A clear, simple example, and importantly, a visual schema or diagram.
Keeping it simple and visual.
Exactly. The goal is a solid, uncluttered foundation of declarative knowledge. It uses short microcapsules like 5-8 minutes max, respecting attention spans, and a technique called worked example, then fading.
Fading.
You see the full correct example first. Then parts are gradually removed, making you fill in the blanks. This drastically cuts extrinsic load, less mental clutter, so you focus just on understanding the core concept. Neuroscientifically, it engages the prefrontal cortex for logic and visual areas, creates strong mental anchors.
Building a clear mental picture. Okay, that tackles the overload problem. Then O for operate.
Yes, operate. This is the immediate antidote to passive watching. Right after conceptualize, you immediately practice. You write code in a guided environment with a clear, specific goal.
Hands-on instantly.
Instantly. It forces your brain from spectator to actor. Starts converting that declarative what into procedural how. The guided environment stops you from getting lost on a blank page, gives just enough support. Neurologically, this fires up the motor cortex and cerebellum areas crucial for procedural memory, for skill automation. It's literally building the muscle memory for coding.
Ingraining the how, as you said. Next is D for debug. This sounds critical given how much time developers spend debugging.
Absolutely critical. D is debug. Here you actively learn to find and fix typical errors. You learn to understand those often cryptic compiler messages. The method even deliberately introduces you to common bug seeds.
Throws bugs at you on purpose.
In a controlled way, yes. And gives you tools like an error journal. It reframes errors completely, not as failures, but as essential learning opportunities. Builds resilience, systematic problem-solving skills. This hits the analytical prefrontal cortex hard, training that methodical approach every developer needs.
Turning frustration into learning. Makes sense. Then E for explain. How does explaining help you code better?
E is explain. This is powerful. You have to reformulate the concept in your own words. Write a justification for your code. Or even try to teach it to an imaginary peer. It's inspired by the Feynman technique. If you can't explain it simply, you don't truly get it.
Forces you to really process it.
Deeply. It engages the generation effect. Retrieving and articulating knowledge solidifies it way better than just recognizing it. It's the ultimate test of understanding, turning passive knowledge into active mastery. Neuro-wise, it activates language centers like Broca's area, semantic memory. Verbalizing literally strengthens the neural pathways.
If you can teach it, you own it. Got it. And the last one, X for explore.
X is explore. This is about ensuring the skill isn't brittle. You take the concept you just learned through CODE and apply it in new, different contexts. Vary the situations. Tackle mini projects with increasing complexity.
Making sure you can use it flexibly.
Exactly. It guarantees skill transferability. Building those flexible, robust mental schemas lets you tackle novel, real-world problems later. Avoids that "I can only do exactly what the tutorial showed me" problem. This engages brain networks linked to creativity and synthesis, like the default mode network. You're building adaptable expertise.
Wow. Okay, that codex loop sounds incredibly thorough. Beyond the loop itself, what makes this whole approach stand out as novel and effective compared to everything else?
Several things layer on top of the loop. First, multi-layered feedback. Not just correct, but automated tests, code-style linters, progressive hints if you're stuck, even structured peer review. Second, personalized anchoring. The system tracks your specific error patterns and forgetting curve, then generates personalized revision cards. You review what you need to when you need to.
Highly adaptive to the individual.
Very. Third, program transfer. Systematically varying the contexts in the explore phase isn't accidental. It's designed to build that flexible problem-solving ability. Fourth, tooled metacognition. Those error journals, hypothesis tracking for debugging, the explain step. They explicitly teach you how to learn and how to think like a developer.
Building self-awareness.
Right. And finally, early focus on software quality. Things like checklists, thinking about technical debt. They're introduced from the start, building good habits. The whole system is designed to, well, literally rewire your brain for programming, shifting from passive observation to active construction, debugging, and explanation. It's engineering expertise.
This sounds like a genuinely revolutionary approach, grounded in solid science. But the theory is one thing. Pacta Learning chose Cobol as the first language to apply this method. Given Cobol's reputation, why start there? It seems like a tough test case.
It might seem counterintuitive, but Cobol is actually an ideal fit for Codex. The method's strengths align perfectly with Cobol's specific challenges, turning them into learning advantages. Okay, take Cobol's cognitive verbosity. It's wordy, right? That can easily overload a beginner's working memory. Codex's conceptualized step tackles that directly with visual schemas and breaking things into tiny digestible pieces. It manages that initial cognitive load.
So it makes the verbose nature less intimidating. What about the way Cobol makes you think, that procedural mindset?
Right. Cobol often needs a mental paradigm shift away from modern object-oriented thinking. Codex facilitates this. It provides historical context, uses modern analogies, and crucially, that immediate operate step gets you thinking procedurally through doing, not just reading about it.
Accelerates that shift.
Exactly. And maybe most importantly, a huge part of real-world Cobol work is legacy code maintenance.
Dealing with old code.
Yes. Codex prepares you directly for this. The debug phase teaches you to understand typical errors in old code. The explore phase exposes you to varied mainframe contexts and existing code examples. It's like Codex was made for Cobol's challenges, preparing learners for the actual job.
That makes a lot of sense. It's perfectly aligned. So what does the actual Pacta Learning Cobol platform look like? What features make it brain-friendly?
The platform itself is pretty sophisticated, integrating these principles deeply. First, multilingual adaptability. This comes from Pacta's background in legal publishing. It means high-quality, automatic translation of everything in the browser, lessons, instructions, code comments.
Eliminates language barriers.
Completely. Plus, cultural adaptation dates, currencies match your locale, and an integrated multilingual technical glossary. It removes all that cognitive load of language translation, so you focus purely on the code.
That's huge for global access. What about making the learning itself easier on the brain?
Yeah, enhanced cognitive accessibility. It has intelligent text-to-speech, optimized for reading code aloud correctly, adaptive reading speed. It slows down on tricky parts, speeds up when you're getting it, contextual pauses for thinking, on-demand rereading.
Supports different learning styles and reduces fatigue.
Precisely. Then there's the scientific microlearning structure. Every module is short, 7-12 minutes max. Single, clear goal. Measurable progress. And feedback within 200 milliseconds. Super fast. Prevents overload, keeps you engaged, matches attention spans.
And spaced repetition, you mentioned that's key for memory.
Absolutely. It uses an algorithmic spaced repetition system. It's smart. It tracks your speed, your error types, calculates your personal forgetting curve. Then it schedules reviews optimally day 1, day 3, day 7, day 21, etc.
Focusing review on your weak spots.
Exactly. Ensures knowledge sticks long-term, freeing up your working memory for actual problem solving.
And the quizzes, are they just multiple choice?
No, they're adaptive neurocognitive quizzes. Different question types target different skills. Pattern spotting, predicting code output, fixing errors, optimizing code, applying concepts in context. The system adjusts difficulty based on your performance, even maybe stress levels. And it uses dopaminergic rewards, unpredictable positive feedback to keep motivation high, like a well-designed game.
Keeps you hooked in a positive way. What about actually writing code? Is setup a hassle?
Nope. There's a full integrated development environment, IDE and sandbox, built right into the browser. No complex local setup needed. You get real-time compilation, execution, smart autocomplete. A realistic coding experience without the usual setup frustration. Just log in and code.
Okay, this sounds incredibly well integrated, but the real question, does it work? What are the results? You mentioned faster learning.
The results are pretty striking. We see about a 65% reduction in learning time compared to traditional methods. People master the Cobol basics in around 3 weeks versus maybe 3 months the old way.
3 weeks versus 3 months, that's huge.
It is. And development autonomy, being able to code independently, often happens in 2 months compared to 6 months typically. It really shows the power of aligning teaching with brain science.
That speed is impressive. What about retention? Does the knowledge stick? And can people actually use it on real jobs?
Great questions. Long-term retention is around 85% at 6 months after training. Compare that to maybe 35% for classic methods. That's a massive difference in durability.
Wow.
And skill transfer, the ability to apply it. About 90% successful transfer to actual legacy code maintenance tasks. That's the key real-world skill. And maybe the best indicator, 78% feel capable of teaching concepts to colleagues. That signals deep mastery.
If you can teach it. And what about the experience itself? Less frustrating, more motivating?
The cognitive satisfaction numbers are interesting too, an 80% reduction in reported learning anxiety. It makes a tough subject feel more manageable, less scary, and a 150% increase in intrinsic motivation. People want to keep learning.
That motivation boost is huge.
And maybe the bottom line, the
Yeah.
completion rate. For Pact-to-Codex programs, it's around 92%. Traditional MOOCs often average around 23%, sometimes even lower.
92% versus 23%, that says it all, really.
It really does.
Yeah.
It shows this isn't just another course. It's a system designed to actively engineer expertise, moving people from just consuming information to actually acquiring and retaining skills. #outro.
That is a powerful outcome and a great place to wrap up this really fascinating deep dive. We started with Cobol, this invisible giant holding up so much of our global economy.
Trillions daily, yeah.
Understanding its critical role, its surprising staying power, but also facing the reality of the skills gap, the workforce issues, and seeing how those traditional passive ways of learning, the endless videos, the text-heavy courses just aren't cutting it for building real programming skills.
Can't create that tutorial hell, leaving so many learners frustrated.
Exactly. But then we saw how the Pact-to-Codex method offers this structured neuroscience-based solution, a rigorous framework designed to systematically build durable, practical, transferable skills.
Not just knowledge, but competence.
Right. And Pact-to-Learning's Cobol program, as the first big test case, it really proves the point. It shows that even complex, maybe unfashionable languages like Cobol can be taught effectively, efficiently, even to beginners, with measurable, impressive results.
It's setting a new benchmark, really. A global reference point for how to teach programming effectively, moving beyond passive consumption.
It is. It's a powerful alternative to getting lost online.
Yeah.
It represents a genuinely new standard built for how our brains actually learn. And maybe that leaves us with a final thought for you, the listener. As our world gets more complex, digitally driven, the question isn't just what we need to learn, but how we learn it most effectively. Could actively training your brain, using methods aligned with its natural processes, instead of just passively absorbing information, could that be the real secret to mastering any complex skill, not just coding?
Shifting from content delivery to cognitive training.
Yeah. Maybe the future of learning isn't just about more content, about fundamentally smarter methods, methods that respect and leverage how you learn best.
A lot to think about there.
Definitely. An invisible infrastructure, a hidden job market, and a totally fresh way to approach learning. We hope this deep dive gave you plenty to chew on and maybe even some inspiration for building your own expertise, whatever field that might be in. Thanks for joining us on the deep dive.